Welcome. Today's lesson is entitled Compositions of Functions. Compositions is sometimes known as the fifth operation of combining two functions together to create a third. You've obviously in the past worked with the other four, being addition, subtraction, multiplication, and division. And so now what we're going to do is kind of take a look at a concrete example of what it means to have a composition of functions, and then some of the algebra obviously behind it. So let's go ahead and dive right in. There's a little investigation at the top of your page here to kind of get us thinking about what it means and what I want you to think about before we actually get into the nuts and bolts part of it. So the investigation reads, a patient is given a drug with the side effect of raising the heart rate. All right, easy enough scenario here. And what we're going to have is just some variable quantities that we're going to compare. So if you notice, two variable quantities related together, and we've got some values distributed in a table just off to the side here. So we're going to have the drug level and the heart rate. So again, just think about the scenario for a moment. And these would be two variable quantities that would relate together in this particular situation. Well, what I'd ask you to do before we kind of come up with a conclusion is just think for yourself for a moment, which would be the input of the function, which would be the output of the function. Okay, think about the way we've talked about functions. So which is the input, which is the output? Now I think of it all as dependence. You know, functions are all about one quantity depending on another quantity. And I hope you would agree with me that in this situation, in this scenario, the heart rate would probably depend on the drug level. And so this is a function of this. As a result, this would be the output as a function of the input. So just kind of write that off to the side. I didn't do a fantastic job separating that, but you get the idea. All right, perfect. So heart rate is a function of the drug level. I guess that's the conclusion. I'm going to write it in a slightly different way, but let's go ahead and put that in place. Heart rate is dependent. Let's talk about that notion of dependence. So heart rate is dependent on the drug level. And we'll look at those values momentarily before moving right on to the next piece. So you can see heart rate, drug level, et cetera, as the drug level increases, so does the heart rate. All right. Now, we've got another two variable quantities that would be connected in a scenario like this. So again, patient is given a drug with the side effect of raising the heart rate. All good. Now we look at this. The time and the drug level can be related together. And I would ask you to do the exact same thing. Which would depend on which? Which is the input and which is the output? So think a moment if you would. And the way I thought about it in terms of dependence is that the drug level would be dependent on the time that it was in the system. So drug level depends on time, so output depends on input. Throw that into the mix if you would. All right, very nice. So conclusion for table 2 then. Here's how I would write it. The drug level, which was one of the variable quantities, is dependent on time. All right, so now what we're going to try to do is connect. We basically have two functions. You know, one function up here relating the heart rate and drug level. Another function right here relating the drug level and time. What I want to do is somehow morph those together, to connect those, to combine those into another function. And so here's how we're going to write it. Obviously, I've got 3 lines just down here to get us thinking about it. And then here's what I have. So I'm summarizing from table 1. Heart rate, I wrote dependent before. I'm going to write it as a function here. So heart rate is a function of that drug level. Put that into line 1 if you would. Awesome. And then what I want you to do, in fact, you can get rid of that period right there. We're just going to go free form. All right. And then what I want you to do is put in an and. Underline it. Table 2. I would say the drug level is a function of time. And then a little comma here maybe, and what I want you to write is the word so. And I want you to come up with the conclusion. That would be the ideal. So I'm going to read it slowly one time, and I want you to see if you can combine anything together that would make logistical sense here. So, the heart rate is a function of the drug level. And that same drug level is a function of time. So would you agree with me that there is then a connection between the heart rate and time? And that's what I want you to write in. So as a result, heart rate is a function of time. Now we're going to track this a little bit. So inputs and outputs. So remember, output is always a function of the input. So that is our outputs. Time will be our input. And I'll show you this. You could do this a couple different ways. I'm not going to dive too deeply into this. But what I want us to do is look at these two tables and kind of track it and see if it makes pretty decent sense. So what I'm thinking is time, we're going to start out as our input, right? So I'm going to pick one just sort of random here. I think one that works nicely. Let's start right here. So if you look at that, 1 hour. Can I track that 1 hour, that time component, and can I get to a spot where I actually have the heart rate? So input is time. Can I connect from those two tables in order to get an output of the heart rate? Well, if you look at this, input is 1. Output is 200. So in this particular function, input and output. Now if you notice, up at this top one, that same drug level, which was the output over here, is the input of this function. And that's what I want you to take from this. So let's track that. 1 hour, 200 milligrams. Now we go up here, everybody, and find 200 milligrams. There it is. If I have an input of this function of 200 milligrams, do I now have the heart rate, the final output? Absolutely. So that's sort of the premise. This drug level right here, which was the output of one function, is the input of the secondary function. And so when I started out with time of 1, I got a heart rate of 100. And if you notice in this table right here, look what I'm relating, time and heart rate. And if you notice, 1 hour, 100 beats per minute. 1 goes to 200, 200 goes to 100. I use those, I combine those together now to create this function, combined together, relating heart rate and time. Yeah, pretty neat. I like that little example there. Now obviously we're going to go through some notational pieces and we're going to go through some algebra with it, but I guess let's clarify that and then take one step at a time. So first of all, this situation is an example of a compositions of functions. Okay, perfect. And I'll explain exactly what I want you to really get out of that. And it very simply, the output of one function here we go, becomes the input of a second function. All right, so write that in, and then we'll see it play out. Second function, there we go. Perfect. So that's what I wanted you to kind of take from that idea of the drug level. It was the output of one, and it became the input of another. Now, if you think about the 5 operations dealing with functions, addition, subtraction, multiplication, division, and now compositions, this is the only one that really can't be dealt with just numbers, right? There's no inputs, outputs when dealing with numbers. So it's sort of, that's why it's its own lesson here, because it's sort of a little different in the way we're going to process it. I would say, before we kind of dive into the notation piece, is think of it almost as substitution as we go through this. So think of this as a substitution operation. Maybe that'll help. All right, cool. Here's what I'm thinking. let's get into the notation here. So there are two types of notation for compositions. One is this open circle right here. Some teachers like to call that fog, but I don't really use that very often. Truth be told, I like this one because it really, to me, this has the whole premise of the output of one function being the input of a secondary function. So you're going to see me use this one right here. If for whatever reason you happen to see that open circle, that's not multiplication, but that is what's called decompositions. So we would read this, by the way, and I do want to kind of put that somewhere here. Let's do it right here, I suppose. We would read this as f composed of g of x. I like that. Put that in if you would. That's how we would kind of read this notation right here. And obviously you can play around with all these. Here's one for goff. I don't like the way that plays out, but you get the idea. You'll see me use it this way. So this would be g composed of f of x. Very nice. Now at the end of the day, in terms of the flowchart, which I think is very vital to our purposes here, you don't have to underline that, but just for my sake, I think I'm going to just do this one right here. All right, so obviously we can do this a whole bunch of different ways, combine all sorts of functions together. I'm going to ignore the g composed of f of x when I do my flowchart here. So just make a little arrow coming on down, and I'll show you what it's going to look like visually. So again, functions are all about inputs and outputs. So we start out with our generic input, just our x. In fact, let's go ahead and throw a little input right underneath. And remember what happens. That x kind of goes through the function machine. So I'm going to draw a little arrow right here. And if you follow this, if you look at this notation, there's our input, right? Well, it looks like that x is going to go through the g function machine. So that's what I'm going to do. Ugh, my artistic abilities get sadder and sadder. Okay, but that'll be our little function machine, and that will be function g. Excellent. And remember, function g just tells us what to do to the input. So it manipulates the input and out pops the output, which we would describe as g of x. X goes in, g of x comes out. All right, that's the output. Now when working with functions, typically we would stop right there, input, output. But now we're going to take it to the second level. So that output, as I wrote in the definition, everybody, becomes the input of the secondary function. So it's not done just yet. Another arrow. Cool. So let's follow. X went into the g function, and I got g of x. Now based on the notation here, I'm really hoping you'll see it. Where does g of x go? Well, it goes into the f function. And so it goes in to that f function. I'll throw the little f right there. And the f function manipulates the g of x. We perform the rules of the f function on g of x, and boom, out pops f composed of that g of x. And that is our final output. Wonderful. Okay. So if you kind of remember the example from before, time was the input. When we manipulated it, we got the drug level. Well, we're not done there. The drug level then gets manipulated here, and we get the heart rate. That drug level was the output of one function and becomes the input of the other function. I hope you now really do see the connection and really the reason that I did that initial investigation. All right, let's go through the algebra. So again, when all said and done, this particular operation, unlike the addition, subtraction, multiplication, and division, which is pretty intuitive, is just really, it's all about substitution. One output substituting in for another input. All right, so letter A on example 1. Find f composed of g of x. So if I look at this, I start with x, it goes into the g function, and I get g of x. Well, if you look at the example itself, isn't g of x already defined? Don't I know what this is? Isn't g of x this right here? I'm going to go ahead and circle that because that is g of x. It says it pretty explicitly right there. Now, if I look at this notation, that g of x becomes the input of what function? Well, it becomes the input of the f function. When I say becomes the input, what I mean by that, everybody, and this is the key, is it replaces the x's of the f function. So g of x replaces the x's of the f function. Do you see that? It replaces, it substitutes. I like that word for it. And that's it. Once we know that this goes in for here and here, I just kind of write it now. So when all's said and done, I'm going to just go ahead and put a little equals right there just for kicks. When this substitutes in for that, instead of x squared, it's 2x plus 5 squared. And then plus, instead of x, it's just 2x plus 5. And then minus 1. That's it, everybody. G of x replaces the inputs of the f function. All right, now we play cleanup, everybody. You guys are experts at this. So don't forget when we do this right here, FOIL, guys. Please FOIL. Don't be silly. Don't be doing just this squared and calling it a day. To move it along, I'm just going to go ahead and tell you what I got when I FOILed. I got a 4x squared. I got a 20x from the outside and inside when I FOILed. And I got 25. Plus this right here, it doesn't matter too much. Can remove the parentheses. And lo and behold, let's see what we end up getting. I've got a 4x squared. How about a 22x? And how about a 29? So combining like terms, got it. All right. Now, again, it's just combining two functions together to create a third. So you can do this in a variety of ways. That's the most basic right there, just f composed of g of x. What about g composed of f of x? So I'm going to do just a touch of erasing. I want you to sort of think about what's going to happen here as I get myself together. What do you think g composed of f of x will look like? If you don't mind, everybody, I'm going to come out here just because I'm running out of space to work vertically. So I might have a little overlap out here. All right, so I look inside. I start with x goes into the f function, and I get f of x. Great. Well, I know f of x, everybody, so I'm going to circle it. It's this. That's f of x. Well, that f of x becomes the input of the g function. That's what it says right here. This becomes the input of that. What it means is very simply it replaces the x's of the g function. In this case, there's just the one right there, and so it goes in. So, hopefully, it's clicking, but this replaces that, and instead of 2 times x, it's 2 times x squared plus x minus 1, close it, plus 5. Let's clean this up. I'll do it 2 steps, although you might be able to do it in 1. Totally up to you. So that goes together nicely. And I get 2x squared plus 2x, and what do you say, plus 3? Very nice. Lots of combinations. So as I'm erasing, I want you to start thinking immediately about part C there. And let me just make sure I don't erase anything important. Okay, looks good. So again, just combining functions. One thing on top of the other right there. So g composed of g of x. That's how we would read this. So I start with x. I get my g, or I should say it this way. X goes into the g function, and I get g of x. What is g of x? It's that. Well, that is going to be the input of the g function. And whenever I say that phrase, what I really mean is it replaces the x's of the g function. So it's almost like this. That whole thing replaces the x's of the g function. Pretty neat. I like that one. Well, in this particular case, it looks like instead of 2 times x, it's 2 times, and I'd love for you to make sure you see this one, it's 2 times 2x plus 5, plus the 5. So you write the exact same function, except this 2x plus 5, the original function, just replaces that right there. When it replaces, I just write everything left to right. 2, new function, x plus 5, or plus 5, excuse me. Okay, we clean it up here. And how does a 4x, maybe plus 15 feel? Cool. Let's do letter D. So letter D, f composed of g of -2. Now, by the way, everyone, there happen to be two ways we could do this. So I'm going to show you kind of the longer way first, and then maybe just kind of dive quickly into the second way. And then at the end, you decide what works for you if I was to give something like this on a practice problem or a quiz or whatever. All right, inputs, outputs. That's what functions are all about, so let's keep that going. I start with -2. In fact, I'm going to do flowchart on this one, not that it matters. And it looks like that -2 is going into the g function. Ugh, getting uglier and uglier there. But oh well. Oh well. -2. It goes into the g function. So what that means, and let me do a little quick erasing. I'm going to just try to do some mental math, if that's all right with you. It looks like -2 goes into the g function. It replaces the x of the g function. So -2 goes right in there. I get 2 times -2 plus 5. So I get -4 plus 5, and that means I get 1. So input, output. Now once we get that 1, that's this. That answer goes into what function? It goes into f. So we don't finish at the 1. We go one more giant step there. It goes right into the f function. And so I look at this, and when I say it goes into the f function, what I mean is it replaces the x's of the f function. So I put my answer, which was 1. I put it right back in here. 1 squared plus 1 minus 1. And it looks like we actually get an answer, coincidentally, of just 1. So I'm hoping visually it's really starting to click. -2 goes into G, you get 1. 1 goes into F, you get 1, and we stop. Theoretically, guys, can I continue with it? Can I make ones that are like F composed of G, composed of F? You know, like, there's no end. We'll try to keep it simple then. There was a second method I promised I'd tell you about. And if you look at this, do you notice you have F composed of G of a particular X value, a particular input? Well, if you look at part A, everybody, didn't I already create a function for F composed of G for all of the X values? Right? Doesn't this kind of look similar to this? This is just a particular input. This is for all the inputs. And here it is. Here's our answer. When I combined these two functions together with this composition, I got this. Now, I'm not going to do it for you, but I would, if you want, take a moment and put -2 back into that combined function, the composition. Put -2 in for the x's here. And I'll give you 2 guesses what you would get. So, if we've already created a function for all the x's, you know, why not just use it? So if you put that particular input in, you should get this output right here. So again, just a couple ways to look at it. Cool. Let's do example 2. Keep this moving along for you. So these two functions they have a particular relationship. So it's the only reason I put this here. So we're going to do F composed of G and G composed of F, and then quickly move on to example 3, which algebraically is a little harder. So F composed of G. That means we take G of X, and it replaces the X of the F function right there. It replaces that input. And so instead of 3 times X, it's 3 times the whole thing over here. And then minus 4. That would be F composed of G of X. Now, if you don't mind, what I'm going to do is, that was F composed of G of X, right? Now we're going to do G composed of F of X. And then I want you to do the simplifying. So what would G composed of F of X look like? Well, F of X is just this thing right here. I circle it. It replaces the x's of that G function. And instead of 1/3 parentheses x, it's 1/3 parentheses 3x minus 4. And then, of course, the plus 4. All right. Take a moment, if you would. And there's something you'll see when you do this, and it actually, it validates the relationship of these two functions, which you will see in the very near future. Okay, I hope you got x for that one if you simplify it, and I hope you got x for that one right there. That one's really kind of cool. So these two functions, f of x as 3x minus 4 and g of x as the 1/3 times the quantity x plus 4, have a very particular relationship, and you will see that coming up. The reason we verify that relationship is through compositions. If you get x in both the compositions, then they have that particular relationship. If you want to look at the very next lesson, you'll see what they are. All right, let's go get example 3. So we've worked with, I don't know, linears and quadratics. Let's get into some more of the heavier functions. So these are two rational functions, and let's give them a try. So part A, good one to do. So part A says f composed of g of 1. So I take the 1, and it goes into the g function. So that would be just straight up going right in here. And I'm hoping you would notice, in fact I'm going to go ahead and maybe flowchart this just a little bit. So 1 goes into the g function. As we all know, first we'll get an answer, hopefully, and then go from there. But in this particular case, maybe you're already ahead of me, but if I try to put 1 in for x right here, do you notice that I've got a problem? I have an undefined situation going on. I can't divide by 0. 4 over 0 is undefined. And so as a result, in fact I'm going to box it up right here, that doesn't happen. Now I want you to keep that in the back of your mind if you would. So f composed of g of 1 cannot happen. All right, remember that if you would. Now let's go get the generic version. So how about f composed of g of x? This is a good one. So in this particular case, g of x, which is this guy right here, is going to replace the x's of the f function. So see if you can do that without me drawing circles and arrows. If you can't, try to draw it on your own. So I've got that. And then again, this goes into both those x's there. So 4 over x minus 1 and then plus 2. Okay, really nice. Now if you remember, we've dealt with compound fractions before, and that's exactly what this is, because I've got smaller fractions within the overall larger fraction. Well, how do I simplify that? I multiply everything. I distribute the numerator and denominator with the LCD. And I hope you do see here that the LCD will be just x minus 1. So I'm going to try to be consistent there. It's getting a little sloppy, but I'll do the best I can of the way I taught it when we did rational expressions. So if the LCD is x minus 1, I'm going to put it over 1. Anything I do to the numerator, I'm going to do to the denominator. So I'm going to distribute it into the parentheses here in the numerator, distribute it into the parentheses in the denominator. And remember, the whole reason for doing this, everybody, is to get rid of this denominator and this denominator right here, because that's what's creating the fractions within fractions. Okay, let's see if you remember how to do it. Again, I love when students work ahead of me. So if this x minus 1 is the problem, right? Well, this x minus 1 on the top is going to cancel out with it, and I fixed the problem. There they go. And all I'm left with is the 4. Here's my plus. Now there's no problem here, right? There's no denominator under that 3, so I can just multiply the 3 times the x minus 1, so I get 3x minus 3. Perfect. And then down below, same idea. That's a problem. It's got to go. So it's good that this is right up here, because those are going to cancel out. And notice I get the 4 again. And then over here, no problem at all, so I just multiply straight across, and I get 2x minus 2. All right, so I'm going to clean this up just a little bit for us, and then we'll pause for a moment and take a look, see what we get. So I get a 3x plus 1 on top, and what do you say, a 2x plus 2 down on the bottom. That looks really, really great. But now, everybody, what I want us to do is focus our attention on part C. It says determine the domain of the composition function. I'm not going to try to be melodramatic about it, but I do want to be very careful with this piece. So, algebraically, I know dealing with rational functions that I potentially have an exclusion that I've got to deal with. And if I look at my answer, I'll focus on the denominator. I'm seeing that I can't make that denominator 0, and if x was -1, that would be a problem. So x simply cannot be -1. And take a moment, if you would, and just write below here. I'm not going to, but if I ask you to do it, from the answer. Just write from the answer just below there. Okay, but now there's another problem. I'm not quite done. Because if you look back just a little bit, look at part A. If you remember, I tried to do something with those two functions, right? I tried to take f composed of g of 1, starting with 1 and going through the two steps in order to get an answer. Well, if you remember, I couldn't even get through step 1 because it was undefined. And so this input right here, even though we don't necessarily see it in our simplified overall answer, is carried over as an exclusion from this right here because it doesn't work. I'm combining these two together. But if you look at this particular input of +1, I can't even get through step 1. And so as a result, everybody, here's what you're going to write, and I'll kind of describe it in a little more detail. X can't be 1 either. Please make a very good mental note on that. And what I want you to write, I'm not going to do it, but I want you to write just underneath that one, from the inside function. Just keep that in mind, and please write that down, from the inside function. Okay, and here's what I mean by inside function, f composed of g of x. So if you notice, everybody, g of x is the inside function. You can almost put that in quotation marks. And if there is a restriction on that inside function, and there is, then that restriction carries over right here. Let's take a step back. If you look, there's my answer, right? Well, how did I get that answer? Well, if I look, I was here, wasn't I? Look at that, everybody. Can't you see it? If you look right there, do you notice that x can't be +1? And this, very simply, is just the unsimplified version of this. And so as a result, x can't be +1. Even though I don't see it here, I see it one step back. And this exclusion carries over into the final answer. All right, I'm just going to quickly formalize it, and then let's move on to the next piece. So I do want you to definitely write that down here, and I hope you wrote those other two things that I asked you to look for as well, with the -1 and the +1 there. So here's what I have. The domain of the composition function. So this is different than other domains you've seen because we've got to take into account what happens at the very beginning from the initial functions. So the domain of the composition is what's called the intersection. And when I say intersection, it must work in both of them. So that's what I mean by that. So it must work in both. So is of the final function and the inside function. And again, I kind of, it's not all that official, so I'm going to just sort of put it in quotes there. But inside function really means what's in the parentheses. So in this case, of course, it was g of x, because that's the inside function. All right, so in this case, I look at my answer. Oh, x can't be -1. But I also look at the inside function, which was this right here. Oh, x can't be +1. And so that exclusion carries over into the final domain. All righty. Let's go get examples 4, 5, and 6, all doing the same thing. So let's just take one quick step back, and then we'll dive into these. Compositions is all about combining two functions together to create a third, and it's done in a very particular way, really through substitution. I guess that's the best way for me to describe it. So composing means combining them together. What I want us to do is reverse the process and decompose. So what if I gave you the final answer and I said, go back and tell me the original two functions. So this is the final answer. What would be the original two functions that would be composed in order to get that? So we're decomposing, and you do this a lot in like a calculus class, but it's sort of interesting. Can you reverse it conceptually? Instead of combining, can you break them apart? So a couple things that I'll have you write in place here, and then we'll go to work. So first and foremost, we're going to do it as this one. So actually kind of circle that piece. F composed of g of x. There's nothing written in stone that says it needs to be that way, but that's how we'll pull it off. And anytime I'm talking about that g of x in the parentheses, in the parentheses inside, think of g of x is really a function within a function. So a function within a function. And so what I want you to do is look at this right here. This is h of x. This is the combined answer. And can you sort of pick apart this a little bit and say, oh, well, that's kind of a function by itself within the overall function. Well, the way I looked at this, I just saw, oh, well, there's an x plus 1 right there. If I had just x plus 1 and threw a y equals, well, that would, of course, be a function. So that g of x, which I can call x plus 1, is sort of a function within this overall function, right? Now the question is, well, what would I put in place here in order to make the composition play out accordingly? So here's what I would say, and I'm going to do it on this side. So just remember that g of x replaces the input of the f function. So whatever g of x is, in the end, guys, all we have to do is think of it as, oh, that's just going to replace the input. So which means whatever you took out, just replace it with x. Now what's kind of cool about this is you can sort of see it. F composed of g of x would mean this replaces the x in that function right there. And if this substituted in for there, I hope you would agree, that's what we would get. Now here's what I love about these problems. There are multiple answers. This one I think was pretty straightforward. I think everybody, for the most part, would kind of lead towards that, although there are other answers. But what I'd like for you to do is try to get a little creative with it. See if you can come up with maybe not just one possibility, but two. So keep this in mind. I'm going to ask you to do this a little bit on your own here, and then I'll catch up with you. So g of x is the function within the function. And all you have to remember is whatever g of x is, just go back to the answer right here and replace that with x. All right. So let's go get 5. So I don't know. I mean, I see, oh, 1 plus x squared. It's kind of a good little function. That, if I put a y equals out in front of it, that would absolutely be a function. So a function within the function. And, well, what would f of x be? So this would have to replace x. So again, whatever this is, now just throw an x in place. And I'm hoping you'd agree that if this went in for x right here, I would get my original. So this is now decomposed. I broke it apart into two functions. It's what's called decomposition. Anyone come up with another answer, just out of curiosity? I'm going to put a little curtain right here. So that's one possibility. I'm looking at this. Is there another maybe function within the function? How about just x squared? You know, y equals x squared is absolutely a function within a function. So as a result, if I pulled this out and just replace it with x, it would be 1 plus x to the third. If that went in here, then I would get this original one right here. Cool. Probably come up with some others, but that's pretty good for now. Let's see if you can do example 6 and at least come up with two possibilities, two of them. All right, here's what I have. So how about this? X cubed minus 4 is definitely a function within the function. So if I take that out and just replace it with x, so instead of x cubed minus 4, I just put x back in, then it should just be this. That's a great one. Anyone come up with another one? I've got another one. How about the absolute value of x cubed minus 4? That's a good one. That's a function within the function, right? Pull this whole thing on out and just replace it with x. So that would be 2x plus 5. Super. Hey, come up with another one. This one's a nice comprehensive function, you could probably come up with a lot. Maybe include the 2. I don't know. I'm just making stuff up at this stage. How about that? Yeah, that's a function within a function. And as a result, if I put x in its place, there we go. Again, I'll bet you can probably come up with some more. Cool. Try some of those when you get a chance. If you have questions on them, great, just ask. But I love that there are different answers for it, so be creative if you can. Last one, example 7. Just a good little quick word problem. A meteorologist is inflating a spherical balloon with helium gas. If the radius is changing at a rate of 1.5 centimeters per second, express the volume as a function of time. All right, I like this. So I'll show you a couple different ways, and then quite frankly, part B, I'm just going to give you the answer as time is of the essence at this stage. So the way I always think about we're talking about functions, inputs, outputs. Volume as a function of time. Output, input. So here's what I'm thinking. Let's start with time, just conceptually. Let's get an idea of what's going on here. And I'm going to call it T. Now, if you look at this, I don't have necessarily a relationship here between time and volume right off the bat. But in the information, especially in part A, if I know how many seconds, then I can probably figure out the radius. So I'm thinking that we can connect time and radius together pretty nicely. It's increasing by 1.5 centimeters every second. So if I know the number of seconds, I very simply have to take that and multiply by 1.5. So I would just say 1.5 t. Wonderful. Now here's the idea. It's a spherical balloon. So radius of a balloon, volume of a balloon, yes, I can connect those. And so now we're starting to think of radius and volume. What do I know about the volume of a sphere? Well, I know that a volume is 4/3. Sorry, let me erase quickly. There we go. Pi r cubed. Okay, but I don't want volume as a function of radius. I want volume as a function of time. So that is the thing that has to get reconciled. How do I fix that? Well, guys, what do we know the radius is? The radius is 1.5 t. And so I'm really hoping it's starting to click that you just see compositions is really just substitution. So 4/3 pi times 1.5 t raised to the third power. Now I'm going to do a little finagling here. Don't stress too much about it. I mean, this looks pretty good, but if I take 1.5 cubed and t cubed and simplify this, humor me for a moment if you would. So I've got the 4/3, and then 1.5 is really 3/2. So I'm thinking of this as 3/2 t cubed. And so 4/3 and then the pi. And if you remember, this is good exponential property work. 3 cubed is 27, 2 cubed is 8, and t cubed is t cubed. And I could start simplifying some things. So a very long story short, the volume is equal to, if I multiply 4/3 times 27/8 and do some simplifying, it happens to be 9/2. Again, don't stress about that. I'm just rushing through the end here. But that would be a fantastic answer. If you got this far, again, that's good. I would always encourage you to stretch yourself in terms of algebraic simplification. All right. Well, everybody, part B, I told you I just wanted to give you the answer here. So in this case, I'm looking for the volume after 4 seconds. Look, I connected volume for any time. Well, here I've got the volume for one particular time frame. So volume for 4 seconds just means 4 becomes the input of our function. So 9/2 pi 4 cubed. And again, long story short, this is what I got when I threw it in my calculator. Got about 904 and change, and this would be centimeters cubed. All right, great stuff, everybody. I'm going to stop right there for you. As you work with these, if you have questions on the examples or the practice, you just let me know.